Welcome to my talk on the complexity of bounded context switching with dynamic thread creation for ICALP 2020. I'm Pascal Baumann. This is a collaboration with Rupak Majumdar, Ramanathan Thinniyam, and Georg Zetzsche, and we're from the Max Planck Institute for Software Systems. Let me give a brief introduction, starting with an example program to motivate our result. Say we have a global lock and then a main program that spawns what is called a handler and then another copy of itself upon which it terminates. This way we can have any amount of handlers at any given time. Each handler then processes some information and based on that decides whether to call the procedure A with a 0 or a 1. Afterwards it unlocks the lock L, which it should have locked at some point. Now our procedure A also processes some information and can decide to call itself with a 0 or 1, but also to lock the global lock and then move on to its critical section where it writes out whatever it was called with. Since it then returns, all other instances of A on the call stack will also write out whatever they were called with one after the other, upon which we return to the handler where we unlock the lock. Now, because of the locking mechanism, no two threads will be able to write at the same time. However, if this was not present, one thread could start writing, and then another thread could interject and also begin writing as well, which would be undesired behavior. Now, if we want to model this, our model would need to have the following features to capture the behavior of the example. We need concurrent threads, and we need to be able to spawn them dynamically during execution. Need a finite global memory that all threads can access to simulate something like a global lock. A local stack for each thread to store the procedure codes, for example. And because unboundedly many interruptions of threads would introduce undecidability to the model, we have a bound K on the number of context switches that each thread can make. Now, depending on this bound K, there are some known results in the literature. For K equal to 0, the safety problem for such a model is X-space complete. It was shown by Ganti and Majumdar in 2012. And the safety problem relates to questions such as can two threads write at the same time? For K greater or equal to 1, safety is X-space hard and in 2X space, as shown by Atikur, Jani, and Kadir already in 2009. Our result now closes this remaining complexity gap. Now let me talk about this model in a bit more detail. It's called Dynamic Networks of Concurrent Pushdown Systems, so DCPS. And configurations for this model have a global state, an active thread with a local stack, a context switch number, and then there's also a bag which contains inactive threads that have the same components as the active one. The initial configuration starts in some initial state with a stack just containing an initial stack symbol at context switch number 0 for the active thread, and there are no inactive threads, so the bag is empty. Pushdown behavior, so pop and push, as well as the spawning of new threads is defined using transition rules in this model. So let's say we want to pop a symbol from the stack of the active thread. A rule that would facilitate this looks like this. It goes from one state to another, so G1 to G2, and replaces the A here with an epsilon, so nothing essentially. If we look at this example configuration, then the bag will not matter for this, and only the state and the top of stack of the active thread will change. So we pop the top of stack and we go to G2, as mentioned. The push behavior is very similar. We have a transition rule with the same state change, and the A gets replaced by a CB. Then exactly that happens for the active thread and the global state. G1 to G2, replace the A by a CB. For the spawn behavior, I should note that spawns can be defined additionally for any pushdown transitions, Here we have one transition rule where we just replace the top of the stack, so an A with a C, same state transition as before, and we spawn a new B thread. So now the bag actually matters. And we go to G2, change the A to a C, and the new thread will only have the B as a stack symbol and nothing else, and then be at context switch number 0, which is what it spawns with. The context switch behavior actually is independent of our transition rules, but it has to respect the bound that we talked about. Say it's k equal to 3. Then for this example configuration, we cannot switch in this last thread because it's already at 4, but we can choose to switch in any of the other two, or the model non-deterministically chooses. Let's say it chooses the first one. Then it gets switched in, its configuration does not change. The global state also does not change. However, the active thread that was switched out will have its context switch number increase by 1. And this is also how such a thread with a 4 can even exist in the bag if our bound is 3. Because if we now would switch out this active thread with a 3, it would turn into a thread with a 4. Now, the problem that we're considering for safety of DCPS is called the K-bounded state reachability problem, abbreviated SRPK. Our input is a DCPS and a global state, and we ask, is the state K-bounded reachable in that DCPS? Our main result is that SRPK is 2x space hard for every k greater or equal to 1. And together with the result that we talked about by Atik, Borjani, and Kadir, this gives us 2x space completeness in that case. So how do we prove this lower bound? The idea is to have a 3-step reduction. We start with the termination of triple exponentially bounded counter programs with 0 tests on the counters, and then reduce this to termination of recursive net programs. These programs do not have 0 tests, but they have recursion, and this is a new model which we introduce for this purpose. Then we reduce the coverability for transducer-defined Petri nets. This is also a new model. It succinctly defines Petri nets by accepting their transitions using transducers. And then we reduce to SRP1. For the first 2 steps, we adapt the Lipton construction, which was originally used to prove X space hardness of Petri net coverability. So we lift this to 2X space. And for the last part, we need new techniques, which is why we focus on that one first. Now let me introduce transducer-defined Petri nets. It's a succinct representation of Petri nets, as I mentioned, and each Petri net place here is assigned an address, which is a word over an alphabet in this case. So let's say we have addresses of length 3, and the addresses will always have uniform length for these 3 places. Then a Petri net transition would correspond to vectors of such addresses, namely of the places it's connected to. So this transition would have the 3 addresses of the places it connects to as a vector. Now, these vectors will then be accepted by transducers. And this is basically done looking at this vector like a matrix, so column by column. And then the transducer starts from an initial state, like a finite state automaton, and accepts vectors of 1 symbol length on its transitions, and then moves to a final state. So the problem here is that these vectors do not distinguish input and output. So if we have a vector of 3 places, 2 could be input places, 1 output place, or the other way around. To remedy this, the solution is to have 3 transducers for 3 types of transitions, and we only need these 3 types of transitions. So the join type, where we have 2 input places and 1 output place, the fork type, where we have 1 input place and 2 output places, and the move type, where we just have 1 place each for input and output. A TDPN consists of these 3 transducers, but also 2 addresses. The first one is defines the initial marking, 1 token on that place, And the second one defines the final marking, which is used as input for the coverability problem, also just one token on the place with that address. So to simulate this via DCPS, we represent the TDPN tokens using threads. So a token on a place with address W corresponds to a thread with W on its stack, as seen here. This place, A1 to AL is its address, has a token, and this is represented by this thread with A1 to AL on its stack. And usually all these threads will be at context switch number 1. Give another example. Let's say we have these 3 places. Then this corresponds to these 4 threads because the second one has 2 tokens. So there are also 2 threads with that address. And then during certain parts of the simulation, a certain thread might become active and not be in the bag. So let's say we have this move transition that we want to simulate in this setting from CAA to BBD. When we first start with the transition simulation is the so-called read stage, where we remove the input token and save the address symbols in the back. So let's say our input token thread is active, CAA, we are in state main. We remove its first symbol and we save in the back. The color red signifies that it's the input token, the symbol C, and 1 says first position in the address. We do this for the 2 A's, so A2 and A3, second and third position. And then we also spawn a completely new thread with a gamma. And this one will be used in the next stage. This is the guess stage where we work with the output token. And basically we guess it, also saving its address symbol. So we build it from the ground up. And this is what we use that thread for. So we swap it in. This thread that we swap out has the empty stack, so we don't really consider it anymore. And then we have to start from the bottom, so with the last symbol. But since our addresses have uniform length, we always know in this case is the third symbol. So D3, the color blue, signifies that it's the output token here. And then we continue for the 2 B's, so B2 and B1. And also, I haven't shown any global states here, but the idea is that these somehow preserve this control flow of the simulation. So the third and last stage is the verify stage. And this transition would be accepted by tmove like this, such a run. And the idea here is to verify correspondence to such a run by using these symbol threads in the back. So let's say we switch the first one in, or just the C1, and we switch out the BBD that we created, and it goes to context switch number 1. So this is how that happens. And then we remove the symbol and basically save the information, mainly the C in the global state. Then we swap in the B1, and because it also has a 1, so it's the first symbol of the output token. And then we know that there's this CB transition. So since there's such a transition there, we can remove this symbol and continue on. And basically, we do this for all the 3 transitions of tmove here, or if we have longer addresses, then even more than that. And we continue until the very last symbol, which will be this D3 for the AD transition. And since this leads to a final state, we instead of doing anything else, just go back to main. And from here, we can start the simulation again by swapping in any token. And this is how we could assume that our input token was already the active thread. Now we need to handle the other transducers as well, so not only move. They require some slight changes. So tjoin requires basically the read stage to be done twice, another thread stack to be emptied. tfork requires 2 guess stages. We guess another stack. And both of them then need 3 sets of symbol threads in the back. So imagine a third set of threads that are colored in purple or something. And then the initial and final markings have to be handled. Let's say we start in A1 to AL as our W in it. Then we basically build this up from the bottom at the start. So init L will be our initial state, and we go all the way to init 2 until the second symbol, and then we put the first symbol on top and go to main. And this is the only instance where actually a token thread with context switch number 0 can be active in main, but this doesn't break anything. And yeah, for the final marking, so W final, we at any time in main can guess that we're already there. And then we just start removing symbols from the top and checking that these match to our W final. Using these check states, if they do, we eventually end up in the state halt, which we will use as input for our SRP1. And in fact, this already completes the reduction to SRP1 because all the threads that we use had at most context switch number 1. So now we would continue with the first part of the reduction. I should, however, mention that instead of using RNP, one could use a model called chain systems and reduce from there to TDPN. And Demri, Figuera, and Praveen have already proven that a problem regarding this model is 2x space hard, using similar techniques as we do, but we were not aware of their paper prior to submission. So let us continue the original avenue. RNP are interesting anyway. So we want to adapt the Lipton construction. So let me quickly speak to the original. This was done by Lipton in 1976, and we follow the explanation by Esparza from 1998. It reduces from doubly exponential bounded counter programs to show X space hardness, so bounded by 2 to the 2 to the n with n given in unary. And the question is, can the halt command be reached? It reduces to the same question for net programs, non-recursive net programs. So these do not have recursion. Here counters can't be tested for 0, so one introduces a complement counter for each counter X to remedy this. And X plus this X bar will always be at the bound. And Lipton upholds this invariant throughout. So to test X for 0, one can check that X bar is at the maximum. And to do this, one needs to perform 2 to the n decrements on X bar. And one makes use, or Lipton makes use of the equality that this bound is equal to the bound squared at one level lower, so n minus 1 basically. And then he runs 2 nested loops that many times, and for each loop there's a helper variable that gets decremented and tested for 0 at the end to check that the loops actually do run that many times. So since this helper variable respects this bound at one level lower and also needs to be tested for 0 with a similar procedure, this gives rise to nested 0 tests all the way from level n down to level 0, where you can just decrement a fix 2 times. And then Lipton's program consists of n+1 copies of decrement subroutines for the 0 test, n+1 copies of increment subroutines, because the complement counters need to be initialized at their maximum values in the beginning, and then n+1 copies of the helper variables, which are called y and z for the 2 loops. Now, in our adapted Lipton construction, we have added recursion to this net program model. So we get rid of the duplicate code. We just have one recursive definition for DEC and INC. And we also say that our Y and Z get implicitly copied at each recursion depth. So we work on it on different copies. This way we only need to define them once as well. And to make sure our recursion goes appropriately deep, we define a bound on the recursion depth for RNP. And for X-space hardness, we would use bound n, basically replicating the original Lipton construction. However, we can use the bound 2 to the n to allow triply exponential counter values to be simulated. And we can encode 2 to the n in binary, which is wholly in input space because n was given in unary. And therefore, this neatly lifts this construction to 2x space hardness. And we are done. Now, reducing RNP to TDPN, the last step that we do, the middle step. the idea is to have Petri net places and transitions for the RNP and copied for each recursion depth. So we have one place per counter X and one place per line of code for each recursion depth, and then some auxiliary places as well, which we will talk about in a moment. And then transitions to simulate the commands. So these transition constructions are from Lipton as well. The idea is for an increment command to go from the L1 place, line L1, to the L2 place, line L2, move the token, and then put an additional token on the counter X. Obviously, all of this at recursion depth D. And then the decrement is similar, just takes a token, and the halt moves to a special halt place, does nothing else. This is one of those auxiliary places. The jump, the go-to, just connects two places representing lines of code, and the non-deterministic jump does this twice. So you can choose between either, or the model chooses between either. For the call and return commands, here on the right, let's say we call in line L1 this procedure proc. Before going to L2, the idea is to move to such a waiting place, put a token there that says we're waiting for proc to finish. And then this first transition should also initiate proc. So let's say proc starts in line L3, then it puts a token there, however, at a recursion depth 1 higher, because the call stack now is one more entry. And let's say we return in line L4, then from there we have a transition to a special return place, also an auxiliary place, and this connects back to the second transition above. All transitions that we've shown so far were either of type move, join, or fork, so this works with TDPN. We define our initial marking to correspond to the first line of code at recursion depth 0 naturally, and the final marking will be the auxiliary halting place at depth 0. And we can assume that this will be reached at depth 0, so that also works. Now, to accept all of this with the transducers, the idea is to have binary addresses for places split into two parts, U and V. And U is the role, so which line, which counter, which auxiliary place is this, and V is basically which copy of that is it. So just a binary representation of the recursion depth. And to construct transducers with polynomial many states, a very rough idea is there are only polynomial many possibilities for triples of U. So one has this branching part that is short and wide for that. And then it connects to a long and thin part that just compares recursion depth, whether they are equal or off by 1. And this construction then does the job, which is why we have finished this reduction and in fact the whole proof. And thus, in conclusion, I can say that together with the previously known results, we have shown that SRPK is indeed X-space complete for K equals 0 and 2X-space complete for every other value of K. So there are no remaining complexity gaps. Furthermore, we introduced two new natural models, RNP and TDPN, and since they have X-space complete problems of their own, they might be of independent interest to maybe prove other complexity bounds for other models. And as a bonus, our hardness result can even be applied to an adjacent model. So this is called replicated finite state programs by Kaiser, Krönig, and Wahl from 2010. And this basically has global and local Boolean variables, finitely many, instead of global state and local stack, but is otherwise the same. Thank you for your attention.